Hello, welcome to today's class on Understanding Geography with Diagram. Today the topic is we'll be understanding the physical properties of the ocean water, that is both your salinity, temperature and density. Now, first of all, understand what is salinity. Salinity is nothing but the amount of dissolved substance in the ocean water measured in grams per kg but expressed in parts per thousand. See, whenever we say that the salinity is 34 or 33, we basically say it like this. It means 33 parts per thousand. It's that simple. Next, what are the sources? See, the primary and the major source is your river runoff. What is this river runoff? Basically, what happens is that whenever the river that is flowing out of the continents, what they do is that they carry with them saline minerals like potassium, calcium, and other minerals which are basically derived from the rock that are weathered. Next is your submarine volcanic eruption. Submarine volcanic eruption simply means that the volcanic eruption that is occurring within the ocean. And this is the volcanic eruption that basically results in adding to the salinity of the ocean water. Next is your atmosphere. See, in the atmosphere itself, the atmospheric interaction also is one of the biggest results of your addition of your salinity into the ocean water. Again, last but not the least, it's your biological. What is biological? See, basically what happens is that so many creatures live within your ocean body. Now these creatures, basically what they do is that they deposits all their this excreta within the ocean. Let's say for your fishes itself, they eat within the ocean and also excrete within the ocean. Now such procedure also adds up to the salinity. Now remember this, if there is a source that is adding to the salinity, then there is also a source that is removing the salinity, and such source is called sink. Sink is a natural process, and sink can be natural and can be anthropogenic. Anthropogenic means man-made. Natural, basically we have evaporation. Next we have the salt spray by the tidal surge. Tidal surge simply means that, see, basically you must have seen that whenever in the ocean, this beaches itself, that there would be salt, this white color rock type materials would be found over there. These are nothing but your salts that have come because of the sea wave, sea surge, or your tidal surge. Next is your formation of oceanic ridge. What do you mean by oceanic ridge? Basically, I have already explained in the basic concepts of your oceanography. Now, oceanic ridge, whenever they are being formed, where are they formed? First of all, oceanic ridges are formed where the divergent plate boundary. Now, whenever these oceanic ridges are formed, they absorb calcium, mineral, and potassium salts that basically, hence, reducing the salinity of the ocean water. Last but not least, it's your anthropogenic cause. Anthropogenic cause basically involves that the salt extraction for the consumption. This salt extraction for the consumptions also leads to your decline in your salinity within the ocean. Next, what is the controls of the oceanic salinity? First and foremost, it's your evaporation, or it's your temperature, or it's your sign of latitude. Remember that all these are same. Rise in temperature means rise of the evaporation, and remember that evaporation is directly proportional to salinity. So is the temperature. Greater the temperature, greater is the salinity. Greater the evaporation, greater is your salinity. Hence, as you can see within the equator itself, the salinity, when we are moving from the equator towards the subtropical high, you'd see that the salinity is basically increasing. And from the subtropical high pressure zone, the salinity starts decreasing towards your subpolar low and to your polar high. Similar cases for the northern hemisphere, similar cases from the southern hemisphere. Hence, from this we can conclude that salinity goes on decreasing from the tropics towards the pole. I hope you get it clear. Next, precipitation. See, precipitation is inversely proportional to salinity. Means greater the precipitation, there would be less salinity. Equator, 300 centimeter of rainfall, hence has less salinity. Subtropical high, less rainfall, hence has high salinity. Over here itself you can see the equator, there is a low pressure region, hence more rainfall, therefore the salinity remains low. When compared to the subtropical high, the precipitation is quite low, hence high salinity. Now, with this precipitation, I would first like you to refer to this atmospheric pressure. Again, with respect to atmospheric pressure, look at this: low pressure, heavy precipitation, low salinity. Example is your equator and example is your subpolar low. Similarly, high pressure, low precipitation, high salinity. Example is your subtropical high. Next, move on to your influx of the river water. Greater the influx, lesser the salinity. Example is your Bay of Bengal and the Baltic Sea. See, Bay of Bengal is more continental than Arabian Sea in the figure if you look at it. Now, however, it is the influx of the number of rivers that are flowing from India into the Bay of Bengal that results in the lesser salinity of the Bay of Bengal. Next, less influx of river water, hence more salinity. Example, Arabian Sea and Red Sea. When you compare the Bay of Bengal, the number of rivers that are discharging water into the Bay of Bengal and the Arabian Sea, you will always find that the Bay of Bengal has a larger number of rivers which are discharging the water, hence less salinity. Next, move on to your wind direction. Now remember that wind direction also influences salinity. How? See, wind drives more saline water to less saline water. Example, your trade winds. The trade winds blow out of the subtropical high pressure area. Obviously, I have said that within the subtropical high pressure area, the salinity is high again. Now, this is the reason why the Gulf of California has less salinity than the Gulf of Mexico. Let us understand this via diagram. See, first of all, remember that this is the subtropical high pressure area that basically what happens is that the trade wind comes from. Now, what happens is that this particular Gulf of California, which is located over here, and the Gulf of Mexico is located over here. Within this Gulf of California region, the trade winds basically what they do is that they transfer the more saline water into the less saline water. Hence, as a result of which the salinity in the Gulf of California is less when compared to the Gulf of Mexico. Next, there are also another reasons why the Gulf of Mexico has higher salinity. We'll look into it in the incoming section. Next, the ocean current. Another thing that affects the salinity is your ocean current. Ocean current affects the salinity in two manner. First by inducing the precipitation, and second by transport of water. Let's go on for inducing the precipitation. The eastern side of the continent or the western side of the ocean, we have the warm current, and this warm current leads to your high precipitation, hence low salinity. Over here in the western side of the continent, what happens is that we have the high pressure induced by cold current, hence low precipitation, hence high salinity. You can see this from the diagram itself. This is your Africa, where we have the Mozambique current to the eastern part of Africa, and we have the Benguela current to the western part of Africa. The west, as a result of this warm current, it basically induces the convection, hence precipitation, hence low salinity. So the eastern part of African coast is low saline than the western part. Reason being is the prevalence of the current. Next, transport of water. See, look at this from an example perspective itself. See, this is your equatorial current. This is nothing but your equatorial current. They are called equatorial current because they arise around the equator. Next, this equatorial current, basically what they do is that they are the drivers of the salinity. They carry out the saline water into the Gulf of Mexico. And from the Gulf of Mexico, we have the extension of the Gulf Stream in the form of the North Atlantic Drift. I have written this Gulf Stream, but this is the Gulf Stream and the extension is North Atlantic Drift. Now, North Atlantic Drift, what it does is that it carries the more saline water towards your Arctic region, resulting in the Norwegian Sea, which becomes more saline. Again, see, like this, your equatorial current increases the salinity of your Gulf of Mexico. Similarly, the Gulf Stream from here increases the salinity of your Norwegian Sea. Similarly, we have the Labrador current, which is the cold current that reduces the salinity over here. I hope you understood why. Because the Labrador current, it actually what it brings is that it brings cold water with it, cold or ablated water, fresh water from the glaciers into this region, hence resulting in your decline in the salinity. Remember this, the complexity of this. See, first of all, cold current over there itself, I have said that are inducing salinity, but over here understand that this cold current is actually, Labrador current is actually bringing the ablated water, hence it is reducing your salinity. Next, we have the ice formation. Remember this, Ice formation increases the salinity as the ice formed excludes significant amount of salt from the water. When the ice melts, fresh water or the ablated water enters the ocean, hence lesser the salinity. See, basically what you understood is that ice, when it is being formed, what it does is that it basically extracts the salinity, or it basically throws away the saline or the salt within the water. Means it will exclude the salt within the water when it is being formed. But when the ice again melts, it what will happen, it adds up to the fresh water. So basically what we understood, that with the formation of ice, what happens is that the salinity increases, whereas with the melt of ice, what happens is that salinity decreases. Hence ice formation increases salinity as well as decreases the salinity, hence and remains one of the major factor of the salinity in the polar region. Next is your location. See, within the location itself, we have the tropical region and temperate region, and within the location, we'll be studying about the marginal water bodies. What are these marginal water bodies? Bay of Bengal, Arabian Sea, Gulf of California, Gulf of Mexico. All these are nothing but your marginal water body. What do you, again we have the, when we say that the Pacific Ocean, Indian Ocean, these are your open seas. Now, within this tropical region, what we find is that the marginal water body are more saline than the open seas due to the high temperature prevailing in the marginal water body. Remember that in the tropical region, what happens is that the solar insolation is high upon the land. Hence, the heat that the land gets, it basically dissipates, or it distributes the heat into the water. Hence, the marginal water bodies gets heated first. For example, what is this, that the Arabian Sea, and your Bay of Bengal, basically their salinity as well as temperature both are high. Hence, you'd find that the marginal water body salinity is higher than the open ocean counterpart. In the temperate region, the opposite happens. Why? See, first of all, in the temperate region, the solar insolations are not that high. Number one. Number two, within the temperate region itself, there is a dominance of your glaciers, as a result of which the glacial water also declines the salinity. Hence, in the temperate region, the marginal water bodies are lesser saline than the open seas because of the less temperature, number one, and next is that influx of the ablated water. Now, see, when I say less temperature, where is the less temperature? Less temperature over the continent. Next, salinity distribution. What do we mean by salinity distribution? Salinity distribution basically is nothing but the analysis how the salinity is distributed both in the horizontal and in the vertical manner. In the horizontal context, we'll be reading about latitudinal and the regional salinity distribution. And within the regional, we'll be studying about how the boundary current is nothing but your ocean current, how do they influence the salinity, and the marginal water body, how do they influence the salinity, or how the salinity over here is influenced. Next, within the latitudinal prospect, see, I have drawn this diagram basically for your understanding. Just look into this. See, first of all, this is your equatorial region. This is your equatorial region. See, within this equatorial region, what you see is that the amount of salinity is 32 to 33 parts per thousand. Now, as we move away from the equatorial region, what we see is that the salinity increases because of the high pressure, or I would call this as a subtropical high pressure zone. Similar cases for the southern hemisphere. Again, as we move towards the subpolar low, we see that the salinity further reduces to 34 to 35. Why? Because of the frontal precipitation. I hope you have read in the climatology itself about the frontal precipitation. I have even made a video on that. Basically, I would suggest that if you do not know what frontal precipitation is, please look into your the Köppen's classification as well as your temperate cyclones. Next we have is your polar region. Within the polar region, as you can see, the salinity is 31 to 32 parts per thousand. Why? Basically, of the ablation or the influx of the fresh water from the glacier. I hope you understand that ablated water means that your melted water or the melted water from your glacier. Next, Regional wise, we'll study it in two contexts. First is your boundary current, and second is your marginal water body. Now, within the boundary current of the boundaries of the ocean, see, in context to the boundaries, comma, the warm current in the western boundary of the ocean. Remember, I'm saying western boundary of the ocean. Western boundary of the ocean equals to eastern boundary of the continent, where there is a convectional precipitation, hence low salinity. Warm current in the western boundary of the ocean, convectional precipitation, hence low salinity. Similarly, cold current in the eastern part of the ocean, high pressure induced dry weather, high salinity. Done. Next, look at over here. See, again we have this example. This is the Mozambique channel where the salinity is less when compared to the Walvis Bay where the salinity is high. Where are this? In the Africa, in the west and the eastern part. Similarly, we have the Saragossa Sea. Saragossa Sea is located between the North American continent and the Eurasian continent in the northern Atlantic Ocean. The Saragossa Sea is totally within the gyre circulation. I'll be talking more about this gyre circulation in the coming classes. But for your understanding, gyre is nothing but a circulation which has been formed because of your actions of your oceanic current. This is your equatorial oceanic current, this is your North Atlantic drift, and this is your Canary current. Now they have formed this gyre, and this gyre, basically within this gyre lies your Saragossa Sea, and this Saragossa Sea is highly saline because of the prevailing anti-cyclonic circulation, or I would say because of the prevailing high pressure. Next, marginal water body. See, in the context of the marginal water body, salinity can be analyzed in two locations. One is with respect to continentality, second with respect to the influx of water, and third with respect to the prevailing climate. Continentality, I hope I have already said you that the Mediterranean Sea is highly saline when compared to the Gulf of Mexico, because the Mediterranean Sea is surrounded by more number of continents when compared to your Gulf of Mexico. Similarly, the influx of the water. Again, this has already been explained. I think within this figure itself, you can figure it out. Next, prevailing climate. South China Sea is less saline than the Gulf of California. How? Because of the prevailing climate. See, the Gulf of California, I would say that the temperature of there is quite high when compared to your South China Sea. Hence, as a result of this, the Gulf of California region has lesser salinity when compared to your South China Sea. Next, temperate marginal water body. See, within this temperate marginal water body, this influx of the ablated water remains one of the major reasons for the determining the salinity. Now over here you can see Europe, it's the Gulf of Boothia and the Baltic Sea. I hope you know where the Gulf of Boothia and Baltic Sea is. If you know that, then please comment in the comment section. See, the Gulf of Boothia is more saline when compared to the Gulf of Baltic Sea, which is less saline. See, basically what I said, both Gulf of Boothia and Baltic Sea both are marginal water bodies. Now within this context, look at this, that the Gulf of Boothia is basically, or the Baltic Sea, sorry, in the Baltic Sea, more number of rivers are depositing their water, as a result of which they are less saline. However, there is an exception. NAD means your North Atlantic drift, which leads to the rise in salinity in the Norwegian Sea. I hope you know that because I have already discussed it in the itself over here itself. Next, vertical salinity distribution. See, first of all, note this down, that there is an absence of uniform trend in the vertical salinity distribution. Means that not that the vertical salinity is not similar everywhere, and it may increase or may decrease in salinity with depth. Now with respect to that, please look into this. See, when the low latitude, what happens is that basically we know that within the low latitude the solar insolation is high, and as a result of which the salinity is more, and as we go down the salinity decreases. This opposite happens for the higher latitude, where in the upper surface the salinity is low because of the lower level of insolation, and as a result of which, as we go down, what happens, the salinity increases. This is your increase, this is your decrease side. Now we are going beyond the 1000 meter, we basically find that the salinity remains most of all constant. Now within this, you can see that within this 300 to 1000 meter, I have made this zone as called as the halocline zone. This is your surface, this is your halocline, this is your depth. This is the upper surface, this is the lower surface, we can say. Upper surface, lower surface, and your halocline. We can divide it into three parts: upper surface, halocline, and then we have the lower surface. Within the halocline itself, you can see that basically the in the halocline zone, what happens is that it's the salinity basically fluctuates. It can decrease or it can increase. Next, for your understanding, what is this halocline zone, what is this thermocline zone, and what is this pycnocline zone? See, remember that this is not to be written. Most of you, what they are doing is that they are randomly and blindly writing whatever I have written in the notes. They are not even thinking what to write, what not to write. See, remember that without understanding, if you are writing, you will remember that for a very short period of time. But with understanding, if you are writing, then you'll first of all you'll remember that it for a very long period of time, and secondly, the examiner will be impressed that this person at least knows something and he has not written anything randomly. So avoid random writings. First of all, you'll see that the halocline, the thermocline, and pycnocline. Sorry. See, both the halocline, thermocline, pycnocline are located between 300 to 1000 meter. Majorly located between 300 to 1000 meter within the ocean. And as you can see, halo means saline and cline means your slope. And thermocline, basically you can see is that it again located between 300 to 1000 meters. It's nothing but your temperature. I have already will discuss it while discussing the temperature distribution. Pycnocline, pycno means your density variation. Again, we'll discuss it while discussing your density. Next, the significance of salinity. First of all, salinity remains one of the major determiners of the boiling and freezing point of water. Saline water, remember that, and fresh water, the freezing point of the fresh water is 0 degrees centigrade, whereas compared to saline water is minus 1.9 degrees centigrade. Similarly, the boiling point of the freezing water, fresh water is 100 degrees centigrade, whereas the boiling point of the saline water is more than 100 degrees centigrade. For studying the seawater density, remember that salinity and seawater density are directly proportional. If greater the salinity, greater would be the seawater density. For example, basically you can even experiment this at your home. The saline water, basically you can form the saline water by dissolving the salt within the glass of water, and you can basically see that the saline water actually remains more dense than your fresh water. Next is your salinity determines your evaporation. See, what happens is that basically I said that over here itself you can see that the boiling point of the water or the saline water is 100 degree centigrade, and the boiling point of the saline water is more than 100 degree centigrade. Hence, salinity will determine your evaporation. But again, remember that temperature determines salinity and salinity determines evaporation. All these are interlinked. Rise in temperature will lead to rise in the temperature of the water, hence fall in salinity. Again, the fall in salinity will also be determined salinity will determine that at what temperature will the water start evaporating. Next is your effect on your marine organisms. Basically, you can completely figure it out that how salinity is basically how it depends effects on the marine organism. Basically, the marine organism, what they do is that they breathe through your osmosis. Hence, there is a minimum salinity over which they can survive, and they cannot survive more than that. And in this context, I would say that. In the context of the Dead Sea, see, this sea is called Dead Sea because rarely there is any living creature that you would find in this. But yes, there are bacteria and cyanobacteria that are found in your Dead Sea. But in the Dead Sea, what happens? It's highly saline. Hence, it becomes non-favorable for the marine organisms like fishes to move into those areas. And you know why Dead Sea is highly saline? Because of the temperature factor. Next, temperature of the ocean water. Now understand the temperature of the ocean water means nothing but the amount of heat which is present in the sample of seawater. Again, the sources are both natural and anthropogenic. Natural means we have a major and the minor source. Major source is your solar radiation and the minor source is your submarine volcanism. Next, we have the anthropogenic source. Is nothing but the movement of the sea vessels. What is sea vessels? Sea vessels means your ships, trawlers. They also add up to the temperature of the water. Next, importance of the seawater temperature. See, understanding the role of the seawater in temperature regulation. Number one, seawater temperature determines the salinity and density. Number three, seawater temperature determines again your evaporation and associated weather condition like cyclone, water sprouts, and tornadoes. Remember that water sprout is nothing but a tornado over the ocean is called as a water sprout. If you do not know what a cyclone is and what a tornado is, I would again request you to go back and watch my video. Next, determiners of sea breeze. I hope you know that the sea breeze is nothing but the wind blowing out of the sea during the diurnal day period. Diurnal means during the daytime. Next, to understand the phenomenon of climate change. This is very, very important. See, what happens is that ocean remains one of the major absorbers of the temperature of the earth's surface. Hence, with the rising temperature, the climate change pattern is more likely to affect us. And to understand this climate change, basically we can understand this from the understanding the temperature of the of your oceans. Next, to understand the origin and direction of a planetary wind. Again, if you do not know how the planetary winds, how the temperature is basically determining the planetary winds, I would again suggest you to go back and watch my video. Next, distribution of seawater temperature. Again, vertical and horizontal context. Sorry, horizontal and vertical context. Within this horizontal context itself, first let's take into account the northern hemisphere and the southern hemisphere. See, within the northern hemisphere, the temperature is more because of the dominance of the landscape. Within the southern hemisphere, the temperature is less because of the dominance of the water mass. If you do not know what I am talking about, just look into the map and you will see that in the northern hemisphere there is more land mass than the southern hemisphere, and that determines your temperature. Hence the water or the ocean in the northern hemisphere would have a greater temperature than the ocean in the southern hemisphere. Now remember that again temperature and salinity are also dependent. Greater the temperature, greater the salinity. Hence remember that the northern hemisphere, the salinity is more than the southern hemisphere because of the temperature factor. Next I have written is that the isotherms are irregular. In where? In the northern hemisphere. What are isotherms? Isotherms are nothing but line joining. These are nothing but line joining places with a similar temperature. Now such isotherms that you would find in the northern hemisphere, they're like this, means they are very fluctuating in nature. But on the other hand, the isotherms are more of the regular where in the southern hemisphere, means they completely follow the latitude, means they are in straight, almost in the straight line, but don't write straight line, they are in regular, just write it regular, and that they follow the latitude. Next, latitudinal wise, see, first of all, temperature decreases from the equator towards the pole. This is an obvious thing. Next, prevailing wind. See, two things. First of all, basically we have the idea, that is your sea breeze and your land breeze. See, first understand this sea breeze. Sea breeze is that it basically flows during the night time when the water is cooler and the land is hotter. In this context, what happens is that air blows from your land towards your sea. Sorry, from the sea towards your land. So what the air does is that, or the wind does is that, it basically accumulates your warm water over here. What is this? In the coast. Warm water is accumulated in the coast. Similarly, during the time of the land bridge, what is your land bridge? Land bridge happens during the night time when the lands are cooler than the ocean water body. So during the time of the land bridge, what happens is that this land bridge actually pushes away this warm water. As a result of which, there is an upwelling that takes place. What is upwelling? See, once this warm water is being pushed away, so what will happen? The water at the bottom will rise to the top. As a result of this, you'd find that this portion of the ocean is basically cooler, or the coastal regions are basically cooler because of your upwelling factor. What is upwelling? That is replacement of the cold water. Next, let's look into the global context. See, basically let's talk about this portion that is your trade winds. See, as you can see that the trade winds blow from east to west. Hence, what they do is that they basically decline the temperature over here and increase the temperature over here. Remember this. They decline the temperature over here and increase the temperature over here. Similarly, understand the role of westerlies. Westerlies again they move from west to east, and they decline and the temperature is declined over here where the temperature increases over here. Why? See, from the part from which they move, they actually transport the warm water from with them towards the other direction. Similar is done by the westerlies, and similar thing is done by the trade winds. Hence you can see that the warm water basically is located in your subpolar region, and the subpolar region obviously we know that is known for your frontal climate. Similarly, in the equator itself, what we have in the equator itself we have is that this with the rising temperature leads to the higher precipitation. I hope you get that. Next, ocean current. See, warm current, what happens is that the temperature rises. Example is the North Atlantic drift. Obviously you have known that, I have already talked about it in your salinity portion. This warm current which then what happens that with the rise in temperature, what will happen is that which increases the temperature of the eastern sorry let's start it again, I just got confused. See, the warm current, there is a rise in temperature. See, they basically what they do is that they increase the temperature of the region. Example is your North Atlantic drift. North Atlantic drift, what it basically does is that it moves from your North America towards your Europe. Now, while it increases the temperature over here in the eastern coast of North America, similarly it also increases the temperature over here in the western coast of Europe. Simple. Similarly, the cold current, what it does is that it reduces the temperature of the ocean water temperature. Next, minor factors. Submarine volcanism. Another one is that your longitudinal or the extensive. See, it says that within this that if the water body is longitudinal water bodies have higher salinity than the latitudinal water bodies. Means if the water body is extensive in the longitudinal manner, this is longitude and this is your latitude, then they would have more salinity when compared to the latitudinal wise. So the latitudinal wise, you can see that Mediterranean Sea, its latitudinal wise has lesser salinity than your Gulf of California. Next is your vertical temperature distribution. See, analysis of the vertical temperature distribution shows that maximum temperature of the water at the surface. In accordance to the solar insolation, the ocean can be vertically divided into three zones: 20-meter depth, 200, and beyond 200. This 20-meter depth is nothing but the region where it is effectively heated by your solar radiation. Whereas this 200-meter depth is nothing but your photic zone. What is this photic zone? It's the directly heated by the sun rays. And beyond 200-meter depth is your apophotic zone. What is this apophotic zone? Zone where the solar radiation is unable to penetrate. Next, the vertical distribution of the ocean temperature has the following characteristics. Number one, as per Murray was a geographer. He carried out this climate challenger expedition. He found that temperature decreases with the increasing depth. However, such is not uniform. Decrease in temperature with the increase in depth of the ocean is rapid in the equator than the poles. Why? The question is why? See, in the equator, the temperature of the in the equator or in the tropics, temperature of the surface water is more when compared to the polar region. Hence, as we had seen that the temperature when it is more over there on the surface, then it will continuously decline as we move towards the depth, which has been said over here. So what happens is that now such decrease of the temperature with the increase in depth is rapid in the equator. Means in the equator you will find the temperature is 24 degrees centigrade in the top of the surface, and as we go down then it becomes all of a sudden it becomes 10, means a drastic drop. But in the polar regions what happens is that the temperature is almost 10. If you go down it's 8, if you again go down it's 7. Means the temperature decreases not that drastic when compared with the equatorial regions. Next, the zone of upwelling, that is the area from where the sea surface water is driven away. I have already said that the surface temperature are low and the rate of decrease in temperature with the increasing depth becomes low. So what happens that in the upwelling, basically the warm water is pushed away and then the cold water from the bottom is brought up to the coast, as a result of which the temperature declines. hence results in the rate of decrease of the temperature. Basically, how to, I have already explained this over here. See, what happens is that in the upwelling part itself, first of all, the warm water is pushed away. Next, the cold water from bottom comes and replaces its position. So the cold water is obviously cold. Hence, the temperature decrease from the top to bottom is not that stark, or is not that great. Just like yes. Next, over here is the high temperature is recorded at a greater depth, that is at your Saragossa Sea. Remember that Saragossa Sea, Mediterranean Sea, and your Red Sea. See, what happens is that basically when we go down, what happens is that the temperature decreases. But there are certain exceptions such as your Saragossa Sea, Red Sea, and Mediterranean Sea where the temperature, there is an increase in temperature. For example, in the Mediterranean Sea at the bottom we find 24.4 degrees centigrade, while in the Indian Ocean it is only 1.1 degree centigrade. Next, thermal structure of the ocean water. Thermal structure of the ocean water is nothing but we are dividing the ocean water into three parts: your upper, thermocline, and your lower layer. The upper part is located from the surface up till the 500-meter. Temperature remains 20 to 25 degrees centigrade. This layer is present in the tropical water throughout and develops in the mid latitude in summers only. Next, we have is the thermocline zone. This zone is characterized by rapid change in the temperature. Other types, there are also other types of the thermocline such as your seasonal thermocline, which is present at 40 to 100 meters of depth during the time of the summer season. We also have a diurnal thermocline, which is present at 100 to 10 to 15 meters, that too in the shallow water body. The lower layer is nothing but beyond your 1000 meter. Because of this prevailing low temperature, this region is associated with the dense water mass. What is dense water mass? We'll read about it. Next, density. What is this density? Density is the amount of mass per unit volume of substance expressed in gram per centimeter cube. Controls of density, again temperature, salinity, pressure. Temperature is inversely proportional to density, means with the increase in the temperature there would be a decline in density. Similarly, decrease in the temperature will lead to increase in density. Salinity is directly proportional to density. Greater the salinity, greater will be the density. Pressure is directly proportional to density. However, water being nearly incompressible, I'm not saying incompressible, I'm saying nearly incompressible. Hence, pressure exerts negligible control over the seawater density. Hence, pressure exerts negligible control over your seawater density. Next, density stratification. Number one, see, the surface layer between 100 to 200 meter is the thinnest of all layer, also called as the photic zone. Density in the photic zone is dependent on your location. I hope you get this. In the tropical water, higher solar insolation, hence less density. In the polar water, lower solar insolation, hence high density. Again, further, there is no sharp density gradient, that is change in the density with the depth. Therefore, the absence of the pycnocline zone is the polar region. See, basically I would say that this is not the tropical region, rather make it the equatorial region. Higher solar insolation, hence the water is less dense. In the polar region, lower solar insolation, hence the water is more dense, because it depends upon the temperature factor. Next, further, there is no sharp density gradient, that is a change in the density with the depth. Therefore, the absence of pycnocline zone in the polar region. See, first of all, what happens is that, like the, see, in the equator, again I have said that the temperature of the water, or in the tropics the temperature of the water is more, or temperature of the surface water is more when compared to the other region surface water, like the polar region. So in this context, again what happens is that the temperature decline is not that stark. Stark means not that great, where in the polar region. Hence, there is the absence of such pycnocline zone. Pycnocline is nothing but your density zone. Pycno means your density. Next is the pycnocline layer. The pycnocline line is nothing but your transitional zone between the low density surface water and the high density deep water. What is the characteristics of this pycnocline zone? This pycnocline zone carries about 18% of the total volume of the water of the ocean. Water of the ocean. There is a sharp increase in the density with the depth in the pycnocline. Next, it prevents the vertical mixing of the low density and the high density water masses. Last but not least, pycnocline and thermocline are absent in your polar region due to low insolation. Next, deep layer. It's the high density water mass extending from 1000-meter depth to the bottom. Characteristics: it carries 80% of the volume of the water of the ocean. Next, extreme low temperature in the polar areas, comma, deep layer high density mass is augmented. That is, the deep layer high density mass is augmented by the sinking high density water mass in the polar region. Understand this. From the equator towards the pole, we have the dense water mass which lies in the bottom of the ocean or beyond this 1000 meter. What happens is that in the polar region itself, the greater the density, what happens is that they sink towards the bottom, and with the sinking towards this bottom, they augment this polar region, that is the dense water mass of the polar region, and this dense water mass starts moving towards the equator, hence resulting in the flow of the deep dense water mass from the pole towards the deep dense water mass in the tropics. Next, these are some of the possible questions. One is that salinity and the temperature distribution of the ocean. Next is from the UPSC point of view, we can have such questions: importance of salinity, control of salinity, vertical distribution of salinity, or the relation of the density, salinity, or temperature. Each of this could be within a 10 markers question. This is your 60 marks question for your OPSC point of view. Thank you.